All right, so we just finished up using all of the theorems of Math 3. So remainder theorem, factor theorem, fundamental theorem of algebra, and rational root theorem. Okay, so the first two theorems, remainder theorem, factor theorem, cater to the beginning half of this unit and explains, why factors are what they are, how we factor the results of them. The last two, fundamental theorem of algebra and rational root theorem, is going to help us with this lesson right here, which is all about solutions. Now, just a quick review. By knowing the degree, you know the number of roots of solution, you know the number of roots or solutions that a polynomial has equal to the degree. All right. You can also graph the given polynomial to that's an extra space, I'm sorry. So you can graph the given polynomial to find the real roots, zeros, solutions. The reason I included all three of these here is because it's going to be very big. Depending on who makes the particular question, they may use one word or the other. I wish there would be a little bit more consistency, but it just is the way it is. So a couple of examples we've gone through, we can graph them and we can see a couple, but I've gotten emails saying, oh, well, the degree was 6 and I only saw, 2 or 3 or 4 places where it went around the x-axis or crossed or touched the x-axis. Okay, so if that's the case, you're going to have complex, or what we call our complex zeros or irrational zeros. Irrational zeros are real, but they're ugly. Okay, if somebody's thinking irrationally, they're thinking, not with a clear state of mind. It's all jumbled up. It's ugly. Okay, complex is imaginary. So we worked on these from Math 2. And the way you found these, right, in a way that you would see them as an answer choice on a test, is using the quadratic formula, which is negative b plus or minus square root b squared minus 4ac all over 2a. Okay, so what this means is every polynomial can be reduced down to ax squared plus bx plus or minus c. Okay, so once you get it down to a quadratic, you then use quadratic formula. Now, a quick tip I'm going to share with you. If it only touches, it's multiple roots. If it crosses, it's a single root. All right, and we'll see an example of this once we this one actually might work. So if we want to find all the roots of a given polynomial, first thing you do is go to Desmos and you're going to graph it. Okay, so I'm going to go y is equal to x to the 4th minus 81. I'm going to zoom out, hit home, and I see -3 and 3. All right. So x is equal to -3, and x is equal to +3. All right. So from here, what I want to do is change or simplify this polynomial down to a quadratic. You can do this a couple of ways. The way I like to do it is use synthetic division. So I would go -3, 1, 0, 0, minus 81. And I would go 1, bring down your 1, multiply, add, multiply, add, multiply. I think I messed up here. Four, 3, 2. I did mess up. I left off an extra 0. All right, so that was -27. That's +81. Whoops. So that's -27. These multiply to give you +81, and we add, and I get 0. Now from dividing polynomials, we know this is my remainder, this is my constant, this is degree of 1, this is degree of 2, this is degree of 3. Okay, so I've now used this -3. I'm going to do synthetic division again, this time using my 3, knowing that these are the coefficients. But when I say these, I mean these things right here, okay? So 1, -3, 9, minus 27. I'm not going to use 0 here because it was my remainder. It was what was left over. I'm going to synthetically divide again. Let's see if I can not mess up. Bring it down. 1 times 3 is 3. I add them. That cancels. That's 0. Adds the 9. Multiplies to 27. 0. This is my remainder. This is my constant. Degree of 1. Degree of 2. So I'm going to write this as a polynomial. X squared plus 9. Okay. Because I now have it as a quadratic, I need to find the A, the B, and the C values. Okay. Where A is 1, B goes beside the linear x term, which I don't have in this problem. C is the constant, which is 9. From here, I use quadratic formula. So negative b plus or minus square root b squared minus 4ac all over 2a. And from here, the math isn't hard. It's just a lot of steps, which is what makes it hard. Negative b, so negative 0 plus minus square root b squared, so 0 squared minus 4, a is 1, c is 9, all over 2a, and then a was 1. Negative 0 is 0, so I'm not writing it, so I have plus minus. 0 squared is 0, minus 4 times 1 is 9. Whoa, 4 times 1 is 4 times 9 is 36. All over 2. Plus minus square root negative 36 over 2 is an imaginary number. So plus or minus 3i. let me go back. I occurs whenever you have a negative inside the radical. You bring it out, and then that will leave you just with the square root of 36, which is 6 over 2. And then 6 divided by 2 is 3, and then the I. And remember, with complex from the fundamental theorem of algebra, you must also have the positive and negative version. All right. What you can now do with this is put this back into your original equation. So x to the fourth minus 81. So 3i to the fourth minus 81. 3 to the fourth power is 3 times 3 times 3 times 3, which is 81. I to the fourth minus 81. But because this I to the fourth is here messes us up, I have to simplify I. The rule of I squared equals negative 1. So I have I to the fourth, which is equal to I squared times I squared, which is equal to negative 1 times negative 1. Negative 1 times negative 1 is really equal to 1. So 81 times 1 minus 81, well, it's 81 minus 81, and that is equal to 0. So 3i works. So you'll just have to go back and double check every single one of these. Okay? It's a long process. It's a tough process, but if you have a TI-83, it'll be just a little bit easier because you can do store X enter. If you don't have a TI-83, you'll just have to go back, plug in your values to your given equation, and get your answers.